All right, today we're going to dive deep into the quantum computing revolution, but we're looking at it through a really specific lens, security. And it's fascinating because this incredible new technology, it's actually a two-sided security challenge. First, we've got to protect the super fragile quantum machines we're building. And second, we have to protect our entire digital world from those very same machines. It's a huge puzzle, so let's get into it. So let's just set the stage for a second. Think about this question. We're not just talking about a faster laptop here. We're talking about a fundamentally different kind of machine. One with the power to crack the encryption that protects our banks, to design revolutionary new drugs, and to solve problems we currently think are literally impossible. That's the scale of power we're trying to both harness and defend against. Okay, so to really get a handle on this, you need to see what's called the quantum stack. It's this whole new ecosystem from the quantum chip itself at the very bottom all the way up to the apps you might run at the top. And here's the kicker. Every single one of these new layers introduces brand new security holes that just don't exist in the computers we use every day. Now, this slide really gets to the heart of why it's so different. Our computers run on bits. They're either a 0 or a 1. Simple. But quantum computers use qubits, which can be a 0, a 1, or somehow both at the exact same time. It's a machine built on probability, not certainty. So the big thing to remember here is that this isn't just a souped-up version of what we already have. It's a completely different paradigm for computing. So that brings us to the first and maybe less obvious side of our security dilemma. How do you protect the quantum computer itself? These things are unbelievably powerful, but they're also unbelievably delicate. So check out this map. It shows the new attack surface. And wow, there's a lot going on. If you just follow the path from where a program starts to where it runs on the hardware, you can see that every single step is a potential weak point. An attacker could sneak in to mess with the computation, steal the program itself, or just make the final answer completely wrong. And here is a mind-bending difference. Normally, we think of our data as the secret. But in the quantum world, the program itself, the very design of the quantum circuit, can be the secret sauce, the intellectual property. Think about it. A circuit designed to create a new wonder drug could have the molecular structure embedded in its very design. So if you steal a circuit, you've stolen the invention. The hardware itself? Oh man, it's like a minefield of brand new problems. You have decoherence, which is just a fancy way of saying the qubits can spontaneously forget what they're doing. Then there's crosstalk. That's basically when one qubit starts shouting at its neighbor and messing it up. Even the tiniest physical imperfections can cause huge errors. These aren't software bugs you can just patch. They're problems baked into the very physics of how these machines work. Let's make this feel a bit more real. Picture a quantum computer in the cloud, with different people running their programs on it at the same time. This diagram shows how a bad actor running one program could cleverly schedule their operations to interfere with a different program, a victim's program. It basically forces the victim's circuit to do extra, useless work, which introduces errors that corrupt the final result. And the scariest part? The victim might never even know their calculation was sabotaged. Okay, let's flip the coin. Now we're talking about the threat that gets all the headlines. The one that's, frankly, a bit terrifying. This is about securing our entire digital civilization from a quantum attack. Right now, our digital world is incredibly safe. The standard encryption that protects your online banking, it would take the most powerful supercomputer on Earth about 300 trillion years to crack it. So, for all practical purposes, it's unbreakable. And then there's this. A future fault-tolerant quantum computer is predicted to break that exact same key in about 10 seconds. Just let that sink in for a moment. From 300 trillion years down to 10 seconds. That right there is the quantum threat in a nutshell.
And just to be super clear, this isn't some abstract problem for nerds to worry about. We're talking about the locks on everything you do online. Your bank account, your private messages, corporate trade secrets, even government and military communications. It's all built on a mathematical foundation that a quantum computer could one day turn into sand.
So, with this kind of revolutionary technology on the horizon, another huge problem pops up. How in the world do you protect the inventions themselves? Welcome to the intellectual property dilemma. If you're a quantum innovator, you're basically stuck between a rock and a hard place. You could patent your big idea. That gives you a powerful 20-year monopoly. But you have to publicly reveal exactly how your invention works. And who knows if the tech will even be profitable before your patent runs out. The other option? Keep it a trade secret. That can last forever. But if another company figures it out on their own, well, you're out of luck. Well, what about copyright, you might ask? Yeah, That's not a great fit either. There's this legal idea of low authorship, where courts sometimes see computer programs as being more like functional tools than creative works of art. And when that happens, they can get much weaker protection.
And if that wasn't enough, there's another legal headache called the operability test. In patent law, you have to prove your invention actually works. That sounds reasonable, right? But how do you prove something works when it operates on the bizarre, fuzzy rules of quantum mechanics and pushes the very boundaries of what we thought was possible? It's an incredibly high bar to clear.
Okay, so things sound a bit doom and gloom, right? A fragile new machine on one hand, a world-breaking threat on the other. So what on earth are we doing about it? Well, this brings us to the global race to build a quantum-safe future.
The good news is that people are fighting back on both fronts. To deal with the code-breaker problem, scientists are developing something called post-quantum cryptography, basically new kinds of encryption that are tough enough for both classical and quantum computers. And to protect the machines themselves, they're coming up with clever software tricks like hiding a circuit's true purpose, or splitting it into pieces, and even building defenses right into the hardware itself.
And some of these solutions are just so clever. Take this one, called SQITU. Imagine you have a really valuable AI model you want to run on a quantum computer. Instead of putting the real model up there for anyone to steal, you train two separate decoy models. On their own, as you can see, each one spits out the wrong answer. But the real secret is a key that only you, the user, have. And when you use that key to combine the two wrong answers, you get the one right answer. The IP is never exposed. It's brilliant.
And I want you to know, this isn't some far-off sci-fi future. This race is happening right now. The U.S. National Institute of Standards and Technology, that's NIST, has been working on these quantum-resistant standards for years, and they're expecting to release the first batch in 2024. Why the rush? Because multiple major companies are saying they're aiming to build those code-breaking, fault-tolerant machines by 2030. The clock is absolutely ticking.
Which really leaves us with this one final massive question. We are building machines with the power to break every secret code we rely on. At the same time, we're racing to invent new codes that those machines can't break. The question is, can we build and deploy those new defenses fast enough to protect our future? It's a race between offense and defense, and the security of our entire digital world hangs in the balance.